Okay. So, we were looking at heuristic search, and we saw this algorithm called best first search. So, the way that this algorithm works is that it uses a heuristic function h of n, which gives you an estimate of the distance to the goal. And what essentially best first search does is that it sorts the open list, and so let us say new is a set of nodes that is generated by MoveGen, and the basic difference between best first and the earlier algorithms we saw was that open is modified as follows. So, if you did not have this sort h, then you would simply have append the new nodes to the tail of open, and then its behavior would have been like depth first search. But now what we are doing is that we are sorting on this heuristic function h, so that the best nodes come to the head of the this thing. We always pick a node so that strategy does not change. We always pick the node from the head of the open and then start do all the processing that we do, and eventually add the new nodes to open and sort the open list. Now, when I say sort, we essentially mean conceptually you are sorting it, but of course, from the computational point of view it would be quite silly to sort a open list every time, and what we really do is that instead we maintain open as a priority queue. Which is an efficient way of keep maintaining a sorted list of elements, and you can keep adding new elements to that. Now, if you look at the behavior of best first search, what it does is it starts with some node, then it puts it into closed and adds its successors to the open list. So, the single circles are open and the double circles are closed. Then it picks one of them, whichever has the best h value, and expands that. Now, everything else, everything in single circles is an open list, and it can pick any one of them depending on the h value. So, let us say that it expands this node next, and I am assuming here a branching factor of 4, and the search proceeds in this fashion. Maybe this is the next one that it expands, but since it is always looking at the heuristic function, it is not necessary that it will expand one of these 4. Any one of them could suddenly turn out to be better than the rest, because these might gradually become worse and worse in terms of heuristic value, and it is possible that after this doing this it suddenly goes off in a different direction. So, it expands this, and then maybe it expands this. So, the search can sort of jump around the state space, and this entire list of nodes is essentially the open list. If you can make this out. So, the open list is basically a list of all possible candidates that it has generated, which could be inspected at some later point of time, and it is a global list, and best first search is a global search algorithm. So, what are the properties of this algorithm? That we have looked at properties from 4 perspectives. This is time, space, quality and completeness. So, if you look at this algorithm from these 4 qualities, we can see that it is complete, because the only thing it does differently from depth first search and breadth first search is that it sorts the open list. Otherwise, it will always pick one node from open and expand it and so on and so forth. So, at least for finite spaces it is complete. The quality of the solution, as we saw, is not necessarily an optimal path. So, an example of that is, if this is a start node and it has, let us say, some successors and the goal is somewhere here, then it is likely that this best first search will go along this path. So, maybe it will expand this next, generate its successors, maybe it will expand this, generate its successors and so on. So, it will find some path to the goal which will have some number of nodes, whereas it is possible that this one had a direct link to the goal, in which case it would not have found this path of length 2. And remember that we are not counting, we are not allocating any edge cost, we are assuming simply counting how many states are there in the solution path. In this situation, it will not find the shortest path, which is this one, but it will go in this direction. We also saw in the example that if you have a city map and suddenly there is a river on the way, then the best first search will drive it towards the goal and suddenly see that there is no bridge and it will have to take a detour and find a longer path essentially. So, quality is not guaranteed, you do not necessarily get an optimal path. Now, as to time and space complexity, it really depends upon H. If the heuristic function is good, then it will drive the search towards this goal directly and you will find the goal in linear time requiring linear space essentially. It is like a algorithm which will directly go straight towards the goal essentially. But in practice, of course, that does not happen. In practice, it is very difficult to devise heuristic functions which are so good, and in practice it tends to be exponential. So, this is something that we want to try and fight essentially, that we do not want algorithms which are exponential in nature. So, what can we do to devise algorithms which will require lesser space and lesser time complexity. So, let us look at this variation of this algorithm in which we modify open as follows. We simply do this, that open is the sorted version of the new nodes that we have generated. So, what have we done here? We have thrown away all this nodes that we had generated earlier. So, in this case, the open list is sort of includes this nodes. It is a big list, nodes that we had generated sometime in the past and nodes that we have just generated, everything is included into the open list. So, this is like a search frontier for this node essentially. Whereas, now what we are saying is do not do that, just maintain, just look at the latest nodes that were generated, the newest nodes that were generated and just pick the best amongst them essentially. So, what is the behavior of this algorithm? You start with some search, some start node, and let us assume that we keep track of the parent pointer. You generate the children, you pick one of them, let us say the same heuristic function we are using, we pick this node, but we generate its children, and now this algorithm is saying that the set of candidates is only these children of this node that we have generated, and we have forgotten about those other nodes. So, in effect we have deleted them. So, those nodes no longer exist. So, open, as you can see, is going to be a shorter list. Then we generate the third node from here, generate its children, and we throw away this. So, what has happened with this variation is that the search has access only to the latest nodes that have been generated, only to the neighbors of the current node essentially. In fact, once we are going to do this, we do not even need to sort this thing. We can simply modify the algorithm as follows, that next and next is the name of a node is simply the best of current. Okay. So, essentially what we are saying is that if you are at a current node. So, for example, if this is a current node, then you move to the next node, which is in this, let us say this one. So, this is you are here, and then you simply move to this one essentially, and that is the move that you make here. So, that is current, and this is next essentially, because we do not want to waste time sorting, because we are not going to use those anyway later essentially. Once you have decided that this is the best of this current nodes, you can directly select that, and this can be done in linear time of course. And we just put this in a loop while next is better than current. You just keep doing this, as long as you can see a better node, move to the better node essentially. So, one thing that we have done here is that we have changed the termination criteria. When we were doing best first search, the termination criteria was either goal test or open empty. Which means that either we have found a path to the goal, or there are no more candidates left, in which case there is no path to the goal, because the algorithm is a complete algorithm, and you would terminate in the positive case only when the goal test function returns true essentially. Now, we have this criteria while next is better than current. So, what do we mean by better than? That in the case of heuristic function that we were talking about, it simply means the heuristic value of next is better than the heuristic value of current, and if it is a if the heuristic value of the goal is 0, then it should be lower than the value of the current node essentially. So, we have changed the termination criteria essentially, and we have converted this into an optimization problem. And we are saying that optimize the value of heuristic function. So, instead of a state space search algorithm, we have now converted into an optimization problem and said find the node with the best value of h essentially, and we keep moving forward till we find a better value of h. Now, if you consider this situation where you are blindfolded and you are standing on a slope of a hillside, and you have been told to go to the top of the hill, then what is the algorithm that you would follow is, so this is you standing blindfolded, the algorithm that you would follow is that you would possibly take a step in all directions, well in some discrete set of directions, and then move forward to that direction which seems to be going up essentially. Now, if this is a 2 dimensional world or a 1 dimensional world in which you can only move left or right, then you can see that if you go right you will be going higher, if you go left you will be going lower. So, you go right essentially, which is exactly what this algorithm is doing, that it sort of exploring the neighborhood of the current state and seeing that if there is a better neighbor it moves to that state. Next is best of this thing and you keep doing this till next is better than current essentially. Actually, to be more precise, you should have the check at this stage itself, that you should check whether next is better and then only move to next essentially, but I will leave that as a small exercise to be done. In principle, what you are doing is you are moving along the steepest gradient, and in this example we can say that you are doing steepest gradient ascent. And it is not surprising that this algorithm is actually called hill climbing. So, if I remove this version now, it becomes a little clearer to watch. So, this algorithm is called hill climbing algorithm, and essentially it is analogous to climbing a hill blindfolded, and you just move in the direction of the steepest slope and hope to reach the maxima. So, which means that if you reach here and then you terminate and then you are allowed to open your eyes and
say if we have a local maxima, then we will stop at the local maxima.
Exactly.
How is it that we will ever reach the global maxima?
Exactly. So, that is what I was just about to illustrate here, and so this is a figure that I am trying to draw, that you have done this climbing and you have reached a place where all the neighbors are not better than the current neighbor. So, initially of course, you have a smile on your face saying that you have reached the maxima, but when you open your eyes then this smile turns into a frown, because then you discover that actually the terrain is like this essentially. So, precisely the problem that you are pointing out, that this algorithm will take you to a maxima or a minima if you are minimizing, because it would be analogous, but it will you will get stuck in this local maxima, and that is a problem that comes because of the fact that this algorithm is a local search algorithm. It only looks in the neighborhood of the current state to decide where to go next, unlike the best first search algorithm, which maintain a global list of open candidates and it could always move to a better candidate essentially. But nevertheless, there is much to be said about this algorithm. Why? Because of the complexity issues involved, time and space complexity. Completeness, as you have just observed, it is not complete. So, hill climbing can not take you to the global optima. It is not complete, it will get stuck at the local maxima. Quality of the solution, also you cannot even talk of completeness. So, you can't even talk of quality again, but time and space complexity. So, what is the space complexity of this algorithm?
It's log n. If we take a binary tree, say, in that case it's log n. So, similarly.
No, so by space complexity we mean the size of the open list. How many nodes does it need to keep in the memory?
Only those many number of open nodes which it explored by this heuristic function. This heuristic function says this is the best. So, next on you go on incrementing, only one node at a time is present in the priority queue, 1 plus 4 in this case.
Yeah, 1 plus 4. So, it is constant space complexity. So, this is the single major advantage of this algorithm, is that it requires constant space as opposed to best first and all the other algorithms that we saw, which we said that in general require exponential space. Of course, well, depth first search does not require exponential space, but best first search does essentially. But depth first search of course is we had abandoned because it could not, it had no sense of direction. it would still require exponential time. And hill climbing also gains on time, because it only moves along the gradient, it will stop moving once the gradient becomes negative. And so, in some sense it will require linear time, that it will take a, if it takes n steps, it just about takes those n steps and terminates with that essentially. So, the question is, what is this surface that we are talking about, this hill that we are talking about, where does this surface come from? And the answer is that this surface is defined by the heuristic function that we are using to guide search essentially. So, I would want to take a couple of examples, or one example to illustrate that you can have two different heuristic functions and they will define different surfaces. Now, if the surface of the that you were in the space that you were searching were to be smooth. So, for example, if the search surface were like this, then you can see that this algorithm would have taken you to the global maxima, if that is the global maxima. So, it really depends on the nature of the problem. If the nature of the problem is such that the heuristic function defines a smooth and monotonic surface, then hill climbing will work, otherwise it will get stuck to on a local maxima. So, let us take an example from the blocks world domain, which is a domain which is often used to illustrate many ideas in AI, and the domain consists of a set of children's blocks. So, for example, you may have a set of blocks which are arranged like this. So, you can keep only one block on another block. So, here we have 3 blocks and piled up on one top of the other, and then there is a table, and then we have 2 more blocks piled up like this. So, this is a start state given to us, and the goal state is, let us say, a state which looks like this, that you want A to sit on D and then D to sit on B and E to sit on C, and let E be like this. So, this is a goal state. What are the moves available to you? You have only one move, which we will say is like this: move block X, let us call it, from source to destination, and source can be a top of. So, this move can only be done if you can pick up a block, which means it must be at the top of a stack or on the table, and you can put it down either on the top of another block or on the table essentially. So, the source can be only the top of a stack or the topmost block in the stack, and the destination also can be only a topmost block in the stack. So, for example, in this situation we can do the following moves. We can say move this A to top of D. So, you would get a situation like this. That is one possible move you can make. Then another move you can make is you can put A down. So, this B and C remain like this, D is here and A is here. A third move that you can make is you can move D. So, only A and D are the 2 blocks you can move here, because they are the only ones on the top of the stack. So, you can put D on top of A, whereas E remains here, and the fourth possible move is that you can put D down. So, you will get these are the 4 possible moves essentially. So, this is the neighborhood of this state, and we want to use hill climbing algorithm to decide which state to move to essentially. So, now we need to design a heuristic function. So, what can be a heuristic function that we can use here? So, I want to discuss 2 functions, and they are as follows. The first function says that if a block is sitting on a correct destination block, then you add 1 for that block. What is the destination block? A should be sitting on D, D should be sitting on B, and B should be sitting on C, and C should be on the table, and likewise for E should be on the table. So, let us call this H1 of n. It says add 1 if block on correct. I just use the term block. So, in general we mean either block or the table, and we subtract 1 if it is on a long. So, this gives us a function which only looks at the state. So, the idea of a heuristic function is that it should be computationally cheap essentially. You just look at a state and get a value out of it. So, let us just give heuristic values for all these functions. So, let us start with the goal. So, for this we will have +1 for this, +1 for this, +1 for everything, because everything is on the correct place. So, the heuristic value of the goal is 5 or +5. What about the start state? The start state we will have +1 for this, +1 for this, -1 for this, because A should be on D, but it is on B essentially, +1 for this, -1 for this, because these should be on B in the goal state, but it is sitting on E essentially. So, if you add all this up, you will get a value of +1. Now, what about the other states? So, let us look at this value. This is A, B, C, this ends to +1 here, +1 for this, and -1 for this. So, just let me know if I am making a mistake. This state is +1. Here it is -1 for this, -1 for this, +1 for this, +1 for this. So, this cancels off, and E. So, this is also +1. For this one, +1 for this, +1 for this, -1 for this, +1 for this, -1 for this. So, this is also +1. In this case, it is +1 for this, +1 for this, +1 for this, +1 for this. Notice, because A is sitting on D, and in the goal you want A to be sitting on D, and -1 for this. So, this value turns out to be +3. So, these are the 4 states. This is one state, this is another state, this is the third state, this is the fourth state that this move gen function generates, and the heuristic function tells. So, the algorithm says look at the neighbors, if one of the neighbors is better than, if at least one neighbor is better than the current state, then choose the best among the neighbors. In this example, 3 neighbors are equal to +1. So, we do not consider that, but we consider this one which is better than that. So, the first move hill climbing will make with this heuristic function is this one, it will come here. So, from here what are the options? Again we do the move gen function. So, you can move either B or you can move A. If you move A, one thing is you can go back to this state, you can take A from here and put it on top of B, or you can take A from here and put it down here, which is you will go to this state. The other options are you can take B and put it on A, so you will get this state, and you must tell me the heuristic value of this. So, +1 for this, -1 for this, +1 for this, -1 for this, +1 for this. So, this whole thing comes to +1. So, that is one move from here, and one more move is that you can pick up B and put it down on the table. So, you would get B, C, and A, D, E. So, this is -1 for this, +1 for this, +1, +1 and -1. So, this is also +1, is that correct? So, here we are sitting on a state which has a heuristic value of +3 and it has 4 neighbors. This has a value of +1 we have computed earlier, this has a value of +1 we have computed earlier and these two also have a value of +1. So, you can see that this is a maximum and the algorithm will terminate here without reaching the goal state that we are interested in essentially. So, let us try a different heuristic function and this function is as follows. So, let us call it h2 of n and this says add 1 for every block in a correct structure. So, we are looking at the whole structures that the block is sitting on and subtract 1 for every block. So, the difference between this is that you are adding either you are adding 1 or subtracting 1 in this case. In this you may add up many things. So, you are adding 1 for every block in the correct structure. So, if it is if the entire structure below the block is correct, then for every element in the structure you will add 1. If it is a wrong structure, for every element you will subtract 1 essentially. So, let us look at the let us start with the goal. So, we will start with +1 here, +2 here because it is on C and C is on the table. Likewise, +3 here because D is on B and B is on C and C is on table. So, 3 things below it are correct and +4 here and this is +1. So, this is 10 + 1 11. Let us look at the start state. We will add a +1 for C, +2 for B, -3 for A, because it is on a wrong structure. It should have been on ADBC, it is on ABC, ABC is not a correct structure. So, 3 things below it are wrong. So, we do -3 for here. Likewise, we do -2 for this because it is on a wrong structure and +1 for this essentially. So, this 3 and 3 cancel out, these cancel out. So, this is -1, the start state essentially. The same 4 nodes are generated by the same move gen function, which is that you can move these things. So, let us evaluate the values for these 4 states here. So, in this case, as we have seen, this adds to 0, +1, +2, -3. So, this is 0, this is +1 and this will be -1. So, this will end up 0. In this case, these 3 add up to -0 as before. This will add another -4 to that because it is in a wrong structure which has 4 things below that. So, -4 here +1 here. So, this will be -3. This one +1, +2, +3 for this, +4 for this, -1 for this and -2 for this. So, this will be +1 and this last one which is so +3 for these two, +1 for this 4, -2 for this. So, it becomes 2 and -3 for this. So, it becomes -1, is that correct? Okay, so, now let us pause and look at what this heuristic function is, how is it evaluating the situation. The first heuristic function took this as +1 and this as +3 and this is always +1. So, it thought that this is a good move to make and it made that move essentially. Now, when you look at the problem, you can see that the optimal solution is when you pick up A, put it down somewhere, then pick up D, put it on B, then pick up A and put it on the top. That is the optimal solution. So, the first correct move to make is to pick up A and put it down on the table. And if you look at this second heuristic function H2 that we are looking at, first of all you must notice that it is more discriminative. the first function had only very few set of values, plus 1 here, plus 3 here, and plus 5 there essentially. This one has a value of minus 1 here, plus 11 for this, 0 for this, minus 3 for this, plus 1 for this, and minus 1 for this. All values are different. So, it does not think that they are equivalent states. Not only that, it feels that this is a good state, then this is a next best state, and these two states it considers to be bad actually, because its values are lower essentially. Now, using the algorithm, it has a better state to move it. It was at minus 1, it can see plus 1. So, it will make this move essentially, and that you will notice is the correct move to make. From here, what can it do? It can either pick up A and put it on B, which is going back here, and that you can see is the move it will not make, because it is going from plus 1 to minus 1, or it can pick up A and put it onto D, and that is a state that we have seen here. It can make this move, and that is going from plus 1 to minus 1 again. So, it will not make that move. So, it is not going to pick up A and do something with it. So, A could have put on D, which is going to take it to a bad state, or it could have put it back on B, which is also going to take it to a bad state. So, what about the other possibilities? So, it can either pick up B or it can pick up D. So, let us first take the B case. So, it can pick up D and put it on C, on D, sorry, B, D, E, C, E. That is one possibility, or it can pick up B from here and put it on A, that is the second possibility, and the third possibility is it can put B down. So, these are all B moves that we are looking at. That is the third possible state. So, let us just evaluate these values. So, we have plus 1 for this, minus 1, minus 2 and minus 3 for this. So, that is minus 6. So, this value should be minus 6, is that correct? So, C is plus 1, E is plus 1, 2, D is minus 2, that cancels that. So, minus 3 for this and minus 1 for this. So, minus 4. So, obviously, it is not going to make this move. So, it is sitting at plus 1, just keep that in mind. It is not going to move to minus 1 here or to minus 1 here or to minus 4 here. What are the states, values for these two states? So, this is minus 3, minus 2. So, obviously, these states are worse states. So, it is not going to move from that. So, that leaves us only the D moves. So, let us look at that. So, it can either pick up D and put it on B or on A or put it down. So, there are three possibilities. So, D, B, C, E, A, or it can put D on A, which is B, C, E, E, or lastly it can put D on the ground, on the table. Have I missed out on some block here? It is here B, C, D, E, A. Oh, yeah. So, these are the three possible D moves it can make. It can either put it on D, which is the move we are really looking for, or it can put it on A, or it can put it on the table. So, what is the heuristic value for this? It is minus 1 is plus 1, plus 2 3, minus plus 1 4, minus 1 and minus 2, it will be plus 2. Is that correct? For this state, plus 3 for this, plus 1 4 for this, minus 1 for this and minus 2 for this. So, it will be plus 1. So, remember it was sitting on plus 1. So, it will not go to plus 1 or it will not go, it can go to plus 2, but let us look at this one. So, this is plus 1 plus 2 plus 3, that is plus 6 plus 1 plus 4 minus 1, 6 plus 1 minus 1. So, plus 6. So, you can see that this heuristic function will actually derive the search hill climbing algorithm to make these two moves. First, it will pick up D and put it first it will pick up A and put it on the table, and then it will pick up D and put it on B, and you can see that the heuristic value is going up plus 6. And if you were to take this forward, you can see that this actually leads to the goal state essentially in the next step. Essentially, it will pick up A and put it on top of D, reach a value of plus 1. All other moves will be worse than that essentially. So, what we have seen here is that given a problem to solve. So, what is the problem? It is a block solve problem. You are given some initial configuration and you have some desired configuration and you are given a set of moves. You want to use hill climbing. Both these functions are static evaluation functions, which means they only look at a state and give you a value for that. When we evaluate this plus 1 or this minus 3 or this plus 6 or plus 1, we are not doing any search. We are only looking at this particular state and saying this is a value for this state. Both are static. So, both require constant time in some sense, but one is more perceptive than the other. One is more detailed, one looks at the entire structure, the other one only looks at what the current block is sitting at. And you can see that one search, the first heuristic function takes it to a local maxima, the second one takes it to a global maxima. So, what does that mean? It means that the surface that H1 is defining has local maxima. It is like this, something like this, whereas the surface that this one is defining is smooth essentially. So, one thing that you can do when you are using an algorithm like hill climbing is to try and choose a heuristic function which will define a smooth monotonic surface like this, and then of course, you are done, and you are done at a very inexpensive price. The space requirement is constant, the heuristic function takes constant time, and the time complexity is linear, because it will just keep taking one step in positive direction and eventually come to a stop at the goal. So, that is why hill climbing is such an attractive algorithm, because it allows you to do this thing at constant space and linear time essentially. The catch is, can you find a heuristic function which will define a smooth surface to traverse, for the search to traverse. If you cannot, then you have this problem of getting stuck on a local maxima or a local minima, as the case may be, and then we need to look for algorithms which are variations of hill climbing, which can overcome this problem of getting stuck in a local maxima. So, we will look at that in the next classes, I think. Okay. So, we will stop here.